Hi, everyone. I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy news journalist for over 20 years. This is the behind the scenes interviews with the people who are making the news. And today, I'm joined by Dr. Paul Hickson from the University of British Columbia. Paul, how's it going?
Pretty good, thank you.
Now, the question I always like to ask people is who are you? What do you do?
So I'm a professor at UBC in the Department of Physics and Astronomy. And so what I do mostly is astronomy and astrophysics research. But as part of that, I also work with the development of new kinds of instrumentation that can be used for astronomy. And so a lot of my time, particularly these days, is devoted to this instrumentation aspect.
And what I guess brought you and your work to my attention is the announcement that the Liquid Mirror Telescope has seen first light. And I'll be honest, I wasn't keeping track of the Liquid Mirror Telescope. It was sort of the first light was the first time that I'd heard of it. And that is not normal for me. Like, I am normally in the weeds, play by play, excited about every design doc and specifications document, but yeah, this one came out of left field. So, what is the International Liquid Mirror Telescope? Is that right?
Yeah, that's the name of the project. And so probably not too many people have heard about it. It's been under development for quite a while now. The history of liquid mirrors goes back quite a long time. And a lot of the recent development work of that technology was done in Canada, both at Laval University by Professor Ermanno Bora, and then more recently by my group at UBC. At the same time, there was interest in Europe, and I know that Professor Bora had meetings with Professor Sourdais at Liège University in Belgium, and they decided to go ahead and to build a 4-meter type liquid mirror telescope for astronomy. And that started even before I got involved in the project. So, excuse me, I've got a bit of a cold.
Yeah.
But yeah, so I became involved in that project about 15 years ago or so, maybe more recently, but of that order. And at that time, they had, in fact, identified, they found money to build the project, to build a telescope, identified contractors that would build it, and had found a site in India. And there's an interesting story there. So it turns out that there's a company in Belgium, in Liège, in fact, that specializes in advanced optical systems such as astronomical telescopes. And they were building at the time a 3.6 meter telescope for India that would be located in the Himalayas. And since Professor Sourdais was also at Liège University, it made sense for Amos, this company, to build the liquid mirror telescope that they wanted. And so a deal was struck with ARIES. This is this Aryabhata Institute in northern India. That it's like a government research institution that has telescopes and operates them, and has a number of staff, faculty members who are astronomers and also support students and so on. So they had this 3.6 meter telescope being built and several smaller telescopes. And so it made sense to locate the ILMT at that site.
Right. So describe the instrument.
Yeah, so I should start by describing an astronomical telescope. For ground-based optical astronomy, well, even for space-based optical astronomy, you need to collect lots of light, lots of photons, and focus them onto a sensitive detector. And so that begins with either a large lens or more often a large mirror to collect the light and focus it. And there are different ways of doing this, but the simplest way is to use a parabolic mirror. that gets all the light down to a sharp focus, at least at the center of the field. And so the usual way to do that is to grind and polish a large glass mirror or several smaller glass mirrors and connect them all together with computers so that they act like one single large mirror. And the issue that you're faced with is that the surface of that mirror has to be accurate to a fraction of a wavelength of light. Something like 10 nanometers is typical. And that's pretty hard to achieve. And there's an additional problem in that even if you make the mirror with that accuracy, you have to keep it that way,
right,
that accurately, even as the temperature changes and so on. And so that's why conventional glass mirrors are relatively expensive. They work really well, but they're costly.
Yeah, I have a refractor, and I've owned both.
Yeah.
And I much prefer the refractor because I don't have to collimate it. Like I love being able to just take the thing out, put it out, look through it, and see a nicer view of the night sky. But when I had a reflector, I would have to go and fire a laser down inside of it and make sure that everything is lined up again. And then, a few months later, I would have to collimate it again. And definitely you can see the just whatever, bolts are loosening, the mount is shifting, and the thing is getting a little bit out of alignment. Gravity is working inevitably on it like it does on all of us.
Yeah, that's the price that one pays for the larger collecting area that one can get with a reflecting telescope. The refractor is nice as well because it doesn't generally have a central obscuration, and so you get actually a slightly sharper image.
Right, you don't get that secondary mirror.
Yeah, exactly.
Right in the middle of it. Yeah.
Right. So anyway, one way to make a parabolic mirror that it's a little bit simpler but has, of course, limitations is to rotate a liquid. And this was understood all the way back to Newton. And the problem was that the technology wasn't really available to do this sort of thing to get an accurate surface until quite recently. And so it was Professor Bohr in the 1980s that resurrected this idea and started to look at some of the problems that you have to make a parabolic reflector with a rotating liquid. So first it has to be a shiny liquid, and so mercury is usually the liquid that's used. But you have to protect that surface from vibrations, which would cause waves to form on it. And you have to keep the speed of rotation highly accurately constant. So the idea is that you have this container, this dish, and you pour some mercury in it, and then you rotate it at a constant rate about a vertical axis. So it has to be pointing straight up.
Right.
Gravity is pulling downward. And so you get a balance between gravitational and centrifugal forces that pushes the liquid into this kind of a dish-shaped parabolic form.
And it does follow a parabolic, like a perfect parabola?
Yeah, it does to pretty good accuracy. In fact, very good accuracy. There's slight deviations because the gravitational vector is they're not parallel. They're not exactly parallel all over the surface of the liquid. They actually point towards the center of the Earth.
Right, but you've got mountains and the Earth's geode causing issues. That's really interesting.
Yes.
Okay.
Yes. And then there's other factors, Coriolis force, tides raised by the moon, and so forth, that can all kind of slightly disturb the surface. We wrote a paper back in the 1990s analyzing all of these things and found that none of them matter, at least for the types of mirrors we were talking about.
So none are causing more than a few nanometers of
off of
the perfect parabola. Yeah.
Yeah, the biggest effect, due to the fact that the Earth is a sphere, is that there's a very small change in the focal length of the mirror. It's still a parabola, but slightly different focus, and that change is about 20 microns in the focal length for the ILMT mirror.
Right.
And we just adjust the focus to correct for that.
Right.
Yeah, and all the other things are much, much smaller than that.
It would be fascinating if you reached a point where the gravity from the nearby Himalayan mountains was such an issue that you would have to compensate for that. That would mean you'd made a very sensitive instrument.
Yeah, it actually went into our calculation. We had to, we knew what focal length we wanted for this mirror, exactly 8 meters, and that's the way the telescope was designed. The corrector lens was designed all for this 8 meter focal length. And so the question is, what speed do you rotate the mirror at to achieve that focal length? Well, there's a simple formula, and it's got the acceleration of gravity in it. And so you need to know what's the acceleration of gravity at your observatory. And so, well, geophysicists publish maps and tables of the gravitational anomaly for various places on the Earth. And so we looked this up and found what it was for this part of the Himalayas where the observatory sits, put that into the refinement of the gravitational constant into the formula, and calculated exactly what the rotation speed should be. And it all worked.
That's
the telescope
amazing.
focused properly.
So you mentioned early on the other big downside is that it has to be fixed. You have to run perpendicular to the Earth's gravity. So you're only looking straight up.
Exactly. Yeah, we're looking straight up, but we have a fairly large field of view. It's just about as big as the full moon. And that's provided by an optical corrector, which is a bunch of lenses, 5 of them, in fact, that remove the off-axis aberrations that you're familiar with, such as coma, astigmatism, all of these things. And the corrector that was designed for this telescope actually does more than that. It straightens out star trails. And I have to explain why that's important, and it gets into the details of how the telescope is actually operated. But the combination of this gives us a pretty large field of view. And so as the Earth turns, then the telescope, which is looking straight up, is pointing in different directions in the universe. And so we see everything that is in a strip of sky that passes overhead of the telescope. And that's something like 120 square degrees that we can observe without moving the telescope at all.
And straight up is the best place to look anyway. I mean, the farther you are
Absolutely.
away from the atmospheric haze, the better.
Yeah.
The zenith
Yes.
is the least amount of possible atmosphere that you can be looking through. So it's very
That's
fortunate.
absolutely correct.
Yeah.
Yeah. So that's one of the benefits of this type of observing. There's another benefit, and that is with a conventional telescope, a fraction of the time is spent moving it around, pointing to different things, and then getting it focused and whatever has to be done, acquiring the field properly, and then starting the recording of the integration of the camera. Whereas with a liquid mirror telescope, in principle, all you have to do is to turn it on at the beginning of the night and just let it go, recording data constantly. You don't have to point it. You don't have to worry that it's going in the right direction or anything. You just let the rotation of the Earth scan the sky for you.
So do you get are you taking exposures? I'm trying to think
Yeah. So, with some of the liquid mirror telescopes that we built, we were able to write software that would just continuously read out the detector. So the detector is a CCD camera, is like the kind of thing that you have in an electronic 35 millimeter camera, for example. And it's this chip of silicon, pretty large, about that big. And in it, for the camera we have at the Island T, there are 16 megapixels, so it's 4,000 by 4,000 pixels approximately. And so normally the way you operate these detectors is you have a shutter in front, and you would open the shutter for some time, let the light fall on the detector, and when it falls, it creates electric charge, which gets stored in the silicon. And then at the end of the exposure, you close the shutter and you send electrical signals to the CCD chip to shuffle that charge, move it sideways outwards towards an amplifier where it's measured one charge at a time. So 16 million charges, one after the other, are all measured. And that's stored in the computer and used to construct a digital image
Right.
that you would see and analyze.
That's how you take a photograph with a digital camera. Yeah.
That's the normal method.
Right.
But we can't do that, because if we did, we wouldn't see stars, we'd see star trails. Because during any reasonable length of exposure, you need to expose for some time in order to see fainter objects. And
because
so
you can't track. You can't track the telescope.
You cannot track. No,
right.
The telescope
Okay.
does not track, not mechanically. So we track the CCD electronically. So the way this works, let me see.
But you're just dumping. You're essentially real time dumping all the photons, all the electrons out of your detector, and then just storing them elsewhere.
Sort of, yes. So imagine that this is the detector. Okay, it's actually square, but this is what I've got here.
Yeah.
So we orient it so that the stars, as the Earth is rotating, the stars are moving sideways across the detector. Okay, and as they move across the detector, if we just had a long exposure, you would just see a streak. You'd see a star trail, lots of star trails, and that's not what we want. So what we do is we clock or send these electrical signals constantly to push the charges along the detector. So at the same, I'm trying to get this in the right place, there, at the same speed that the image is moving. Okay, so remember what's happening. The light is falling on the detector, and every photon that hits makes a little electron in the chip there. And we want to push that electron along at the same speed that the image is moving, so we don't get it smeared out.
Yep.
And so that's the operating mode that we use. It's called time delay integration, or TDI.
And so I guess the advantage of this then is, like, you can't overfill one detector and have it spray out into the nearby cells in the detector.
Well, you can if the star's bright enough.
Right, okay. But you are essentially taking one long exposure and then recreating at whatever, you're just gathering all of the data that is falling into the telescope. That's really interesting. I sort of think about, like, when I do astrophotography, you have to fine tune the exposure time depending on what the object is.
Yes.
You don't want to, if you record too long, then you'll blow out certain parts of the image. But if you record too short, then you may not get enough useful data. And so you sort of have to balance that for each object. And so will this technique work for, like, a really long, something very faint, but also something very quick? Like, is it just all things for all? Yeah.
Yeah, the exposure time is actually fixed. It's the length of time that it takes for the star to go from one side of the detector to the other.
Right.
And because that's how long, the electrons are getting generated. That's how long the light is falling on the silicon. And for the LMT, that's about 100 seconds, 102 seconds roughly. So that's our exposure time. It's fixed. Right. That's enough that you have to have a really bright star to saturate the detector in that time. Right. And there's not very many of them in the sky, so we don't have too much of a problem with that. It's long enough that we can see reasonably faint objects, like 20-second magnitude or something. And then we can co-add data from one night to another. So we observe the same strip of sky over and over again, and each night. And so we get a series, we get this long strip of image, and we can align it and add it to that from the previous night to effectively double the exposure time. Or at 3 nights, that triples the exposure time, so you can see fainter still.
How many nights will the same spot in the sky remain in your detector? Yeah,
well, because the Earth is going around the sun, the stars rise about 4 minutes later each night. And so there's this 4-minute shift every night. This little strip is going to be shifted by 4 minutes. It'll come along 4 minutes later. But that still leaves several months where there's a lot of overlap, where you can do this co-adding to get much fainter.
That's really interesting. So now, it's a 4-meter telescope. How does it compare optically to a similar 4-meter class, say, mirror telescope with its secondary system? And then how does it compare with adaptive optics? Because I'm assuming there's no way to do adaptive optics for it on its
Uh,
mirror.
yeah, we've thought about adaptive optics. It's tricky, but there are ways that you might be able to do it, but it is quite complicated. And adaptive optic systems tend to be pretty expensive. And we're looking for sort of a low-cost alternative to big, complicated telescopes. Now, for the question, how does it compare with a conventional mirror? We did optical tests with a 6-meter liquid mirror that we built here near UBC, and found that as long as we protected the surface of the mercury from wind, that the surface was accurate to about 10 nanometers, which is as good as any conventional glass telescope. So the surface accuracy is actually very good, but we have to protect it from the wind. And part of the wind is just due to the fact that the mirror is rotating. And so it's entraining wind just by virtue of its own rotation. And that is enough to cause little waves to appear on the surface of the mercury. So we have to protect it against that. And we do it by stretching this very thin film of optical quality mylar over the whole mirror. It actually rotates with the mirror. So you're looking through the mylar when you see the reflection in the mirror. So that fixes this problem with waves and gives you a very good optical surface. But there is a penalty. Some of the light scatters off that mylar, it gets reflected. It's not anti-reflection coated. And so we lose a little bit of light because of the mylar. It's something like 15, 16% or so. And as a result, it makes the liquid mirror behave like it's slightly smaller in terms of its light collecting ability. Not a lot smaller, like the 4-meter is probably something like 3.8 meters or 3.6, somewhere in that range.
I mean, that's still one of the bigger telescopes in the world. So
it is, yes. And in fact, it's the largest optical telescope in India at the moment.
And I love this idea that you're essentially regrinding your mirror every night. Just by turning it on, you are creating what would take a team of optical engineers in Tucson 5 years to do. You do it in with one flick of a button and a few minutes for the motor to turn up. How much material are you using? How much mercury is happening?
The layer of mercury is right now on the ILMT is about 3.5 millimeters thick, and the total volume is something like 50 liters is what we're using. So the mirror actually just rotates day and night. We just leave it running until at some point it's collected enough dust that we decide, well, it's time to clean it. It's kind of like re-illuminizing telescope mirrors. You do that periodically to improve the reflectivity. If we see that our reflectivity is degrading because of dust collecting on the mirror, then we just stop it. Pump off the mercury, clean the mirror, pump the mercury back on. It's all nice and shiny and fresh, and start the mirror again.
So does the dust float to the top of the mercury?
Well, the dust actually collects on top of the mylar.
Right, of course.
So we're going to do some experiments to see if we can very carefully blow some of the dust off using compressed air without damaging the mylar. That's part of the engineering tests that will be done during the summer in the monsoon season for the ILMT. But normally we just leave the mirror running for a month, 2 months at a time.
And just open it up when you've got clear skies.
Yeah, so the building is quite a bit simpler as well because you don't need a rotating dome. We just have a hatch on the top of the roof that rolls back, slides out of the way to let the light come straight down where it's collected by the primary mirror and then sent up to the detector.
So what is the best job for an observatory like this?
Scientifically, the best thing that it can do is surveys. So we don't have the capability to point to any old object in the sky, your favorite object, for example, because generally it doesn't go overhead at our observatory. So the kinds of science that are done is to look at everything in that strip of sky and see what we can learn from it. So it's a pretty large strip of sky. There are tens of thousands of galaxies. There are thousands of quasars. There are lots of variable objects. And so all of those things are accessible to us. And we record the data continuously each night. And so you have this big data set. And then you have teams of astronomers looking at the data, doing different projects, different studies using those data. So the kinds of things you can do, for example, I mentioned that you can add the images together to get fainters, to see fainter objects, but you can also subtract the images to see what's changed from one night to another. And that's a good way of identifying transient sources, things that are variable, things like supernova, for example, variable stars, even planets transiting around stars, producing small occultations. Anything like that is a time variable can, in principle, be studied by a telescope like the ILMT.
So it really sounds like sort of a light version of the Vera Rubin Observatory, that you're doing this time domain astronomy. Look at it for 3 nights, and you'll detect an asteroid that moved through your field of view that would be useful for follow-on observation, or a supernova that is starting to appear over the course of one night from the next night. And a lot of the same kind of discoveries can be made with this instrument as well as with Vera Rubin. But you're in the northern hemisphere while it's in the southern hemisphere.
Yeah, so the Rubin telescope is very powerful, very flexible, and it has access to a very large area of sky, and which is good, but it's also bad in the sense that, well, it can look anywhere. So it's not going to spend a lot of time looking at one little strip of sky over and over and over again. That's the kind of thing that we can do. Yeah. In fact, that we have to do. And so let's suppose you find something interesting in this strip of sky. Supernova goes off, let's say. So there's a 3.6 meter telescope right next door, a conventional one, where we can just relay that information to the observers on that telescope, and they can point to it and follow it up. So this telescope is good for finding things, and many of those things can be followed up with conventional telescopes.
That's really interesting. Now, you said that right now it's a 4 meter telescope, but UBC has actually worked on a 6 meter version of this same telescope.
Yeah, it's not exactly the same telescope, but it's a similar thing. So as part of the development of the technology of liquid mirrors at UBC that started in the late 1980s, early 1990s, we built a series of mirrors of increasing size, starting with about 2.7 meter diameter, and then a 3 meter mirror that was sent to NASA that they used to look for space debris for 7 years at an observatory in New Mexico. And then we were able to get funding, my research group, to see whether we could extend this to larger diameters. I mean, what's the limit going to be? And we decided we would try to make a 6 meter telescope. Now, the amount of money that we could raise is not enough to build a full-blown astronomical 6 meter telescope on top of a mountain in a remote part of the world.
Right.
So, and people would be crazy to give us money to do that because it's such new, untested technology that we have to demonstrate that the thing actually will work before you can do something like that.
But what is your sense in terms of the scale? Like, to go from a 1 meter telescope to a 5 meter telescope is orders of magnitude in cost. To just maintain that level of optical quality as you grow the size of the mirror just gets orders of magnitude more difficult. As you have a larger pool of mercury and spin it up, how do you think the costs will increase?
Yeah, so you need a larger, more expensive, more stable air bearing to support that extra amount of mercury. You need to build a bigger dish. those costs scale, but you're starting with a relatively small number. So even though it goes up, everything goes up if you're trying to build bigger telescopes. But we're below the curve because of this fact that our surface gets formed automatically. We don't have to have this super high precision machining and so on. One of the things that we discovered is that as you make the mirror bigger, well, the focal length, of course, gets longer for a given rotation, for a given f focal ratio, or f number, if you like. And so the cost of the building would go up. And so there's these other factors that you have to consider, not just the cost of the mirror itself, but all the rest of the parts of the observatory. Now, one thing that we found too that would limit, that might limit the size that we could build on the Earth is these waves due to the wind and so on. And so we hit upon the solution of the Mylar. We know that works for 6 meter. We think it would work for 8 meter. Would it work for 10 meters? Probably. Would it work for 20 meters? Well, we don't know. But
I'd like to find out. Oh, there's a lot of background noise coming from your room. I don't know if it sounds like someone's like doing dishes or something in the background there.
Yeah, I'm just going to close the doors here. That'll be a little bit better. So
yeah, that would be better. Thank you so much. So let's start to consider the future and possibilities of this. So where do you think? I mean, I'm just trying to get a sense. Like you say, it's low cost. If I wanted to build a 4-meter telescope, how much cheaper do you think this costs compared to a traditional 4-meter Newtonian reflector?
Yeah, well, the ILMT is about 1/10 of the cost of the 3.6 meter that's next door.
Wow.
So it's cheaper, but you have to realize that it's more limited than the 3.6 meter.
Yeah, but we'll sort that out in a second. Don't worry, we'll get to that. We'll fix the more limited, because I'm sure you've got ideas about that. So then, let's say we go up to say an 8.1 meter, like something that's equivalent to the Gemini or parts of the Very Large Telescope. Do you think that 1/10 cost continues to scale up, or does it even get better?
Yeah, we even did a study actually for an 8-meter telescope, and we went through a fairly detailed engineering process and costing process, and yeah, it's still roughly 1/10. You end up with most of your money is being spent on a very large, complicated camera, for example, and less money on the telescope itself. So you have to look at the entire project budget when you do something like this. And so we were looking at a wide, this was even before the Vera Rubin telescope, we were looking at a wide field 8-meter telescope that would have sort of a several degree field of view, just paved with CCDs. And the camera costs more than the telescope does.
Right, which is fine, right? Like if instead you spend it's 90% on the mirror and 10% on the detector, and now it's 10% on the mirror and 90% on the detector, I still think that still gets you in the right place. So what do you think are the upper limits of this? Like, the biggest telescope that's under construction right now is the European Extremely Large Telescope. It's going to be 39 meters. There was the Overwhelmingly Large Telescope, which they scrapped that project because it would have cost, $1 billion. And that would have been a 100-meter telescope. And they figured that's the ultimate limit. Like a 100-meter telescope, gravity won't let you go any bigger than that. So what do you think are the actual limits of this?
Well, to me, the most exciting prospect for future large telescopes would be liquid mirror telescope on the moon. And Roger Angel had the same idea.
Yes, I've read the paper. Yeah. I think you got a NIAC grant for that.
We did.
Yeah.
Yes, 2 NIAC grants actually.
Yeah.
And then that was followed up by the Canadian Space Agency to look again at the details of the engineering and how you would do that. But the moon has a lot of advantages. So there's no atmosphere, so to speak. And so we don't have to worry about waves on the mirror and so on. You couldn't use mercury because it would freeze, but you can make ionic liquids, which is kind of like liquid salt. They don't evaporate, and you can make liquids that are liquid at quite low temperatures, and that would be forming the surface of the mirror. And then you can evaporate silver coating on the surface after it's been formed and is already spinning, and that gives you your reflecting surface. And yeah, so that study that we did was quite interesting, and it identified a number of scientific drivers, if you like, for this type of observatory. You could build a 20-meter telescope at the lunar pole. You could, in principle, build a 100-meter telescope at the lunar pole. And it's just a question of cost. But the fact that the liquid mirror is a lot less massive than a conventional telescope mirror means that the cost to put the stuff onto the moon is lower than trying to transport a conventional or parts for a conventional telescope there.
And does the south pole of the moon make the most sense?
To us, it did, because we were mostly interested in the infrared part of the spectrum, because we want to look at distant galaxies, and there the redshift moves most of the energy to the infrared. And so the telescope needs to be cool.
Right.
And so at the south pole of the moon, there are permanent shadows in some of the craters. So you could place your observatory inside the shadow, and it would cool down naturally to a very low temperature, just like the James Webb Space Telescope is doing. And then you could power it by putting solar collectors on a little peak not too far away that is in permanent sunshine. And so you'd have this cold observatory, but a stable source of electrical power year round. And it would be quite a powerful combination.
So back to Earth for one second. So, we talked about the size limits, and as I was starting to imagine bigger and bigger telescopes, you started to shift to other worlds. Do you think there's okay, so like if I have like a really nice, say, 14-inch telescope, it's actually going to not give me a much clearer view of it's like if you have like an 8-meter telescope and you compare that with my 14-inch telescope, the resolution is really limited by the Earth's atmosphere. Like at a certain point, no matter how big you make your telescope, you're not going to get a better view to the distant universe. And that's just the atmosphere is the limiting factor. So if you made a 6-meter, 10-meter, 20-meter, you're going to run against that limit. So let's talk about your ideas for adaptive optics.
Okay, sure. Yeah, so you absolutely have to use adaptive optics for ground-based astronomy with telescopes that are larger than a few meters or so. And so we thought a little bit about how could we do this with liquid mirrors. And at the same time, we were also thinking about how could we defeat the limitation of having to look at the zenith always. And so you could imagine that the telescope is normally pointing straight up, that the mirror is rotating around this vertical axis. And you put your detector there and you see what's direct. Now, what would happen if you were to move the detector sideways a little bit? Then it would see light coming and glancing off at a bit of an angle and coming up and hitting the detector. So you would be seeing a different part of the sky. And by moving the detector, it's almost like pointing the telescope within a certain limited range.
I mean, they do that with spherical telescopes, like Arecibo, right? The Arecibo was a sphere, and so you could move the detector around, and then you're just pointing the telescope.
Yes.
But in this case, you have the tyranny of the parabola.
Okay. So you're completely right. I mean, Arecibo has a spherical aberration corrector to correct for the aberration introduced by the sphere. And then they could just, over a limited range, they can track objects, and that works really well. That corrects the resulting spherical aberration. It's a bit complicated to visualize.
Yep. No, I get it.
But this is the idea.
Right. So essentially, you have a corrector lens that that is turning the parabola into a sphere. I'm sure you've got some kind of aberration, but it gets you pretty close.
Yeah, so the way that works is that you place this sort of corrector lens optically conjugate to the primary mirror. So in other words, you have another lens that makes an image of the primary mirror on this other lens. And then it has a certain shape, somewhat similar to the Schmidt corrector, that makes the parabola look like it's a sphere.
And
then,
and how big is this? How big is this part of the machine compared to?
Yeah, it's not terribly large, so maybe a tenth of the diameter, less than that, even a 20th of the diameter.
Right. Okay. Yeah. So you still have to grind a lens, but it is.
Sure.
Yeah. Can you do it on computer? I mean, I think about like with gravitational lensing, people take the image of distant galaxies and then they use it on computer. They'll sort of pull it back apart. Is there a way to do that as well if you're off axis off of your instrument? Or is it better just do it with a lens?
Well, so it's easier to do it with the lens, partly because with reflecting systems, you have to worry about obscuration and things like this. One mirror getting in the way of another mirror, whereas with a lens, it's a little bit simpler.
Yeah.
And so we actually designed a complete optical system that would allow an 8-meter liquid mirror telescope to track over a field of view of, I think it was a few degrees. And at the same time, once you have these lenses, now you can do adaptive optics. And so included in that is a deformable mirror, 2 deformable mirrors actually.
So you would have like a secondary deformable mirror that you would be able to have the pistons underneath and perform the adaptive optics on the secondary mirror. And in that case, you kind of want a bigger telescope.
So it turned out that the 8-meter was a pretty good size 8-meter telescopes.
Yes, please.
All, sort of in kind of like a fly's eye type of configuration, all with these adaptive optic systems. And they would track objects as they came near the zenith. They'd track them for a while, for maybe 30 minutes or so. And then they go and they pick up another object and track it like that. All with these moving, complicated lens systems and adaptive optics. And then if you want to be even more ambitious, you can combine the light from all of these individual 8-meter telescopes to a single point. And if you are following the technology that
like James Webb is using.
Yes, that's part of it, but it's a little bit more complicated because at least the Webb telescope can point and track without having to change its primary mirror. This is a little bit more like the optical interferometer used at ESO, for example, the VLTI system, where you have underground tunnels and moving mirrors to equalize the distance that the light has to travel from every mirror to get to the center, which is a requirement for you to get really high resolution images. And so in principle, you can combine the light from all of these 8-meter telescopes coherently and achieve the resolution that's comparable to something like a 60-meter telescope.
Right. Yeah. So you're making an interferometer with all of these separate lenses, which is great, or using them individually. What about using them like the issue is just like, how can we get more of the sky? And so can you go bigger with the detector? How far can just having a bigger detector get you with being able to see more of the sky?
Yeah, so our wide field 8-meter design, I think, had a 3-degree field of view. And that's kind of pushing the limit of what you can do. But if you want to cover a larger area of sky, you can just build more telescopes because they're relatively inexpensive compared to conventional telescopes. You could put one at every 10 degrees or every 3 degrees of latitude on the Earth, in principle. And then
zenith is somewhere different for everyone.
Exactly.
Right.
And then you'd be scanning simultaneously with all of these beams.
Yeah. Finally, someone is not afraid to get to get very ambitious. I find I usually have to push people out of their comfort zone, and they're like, no, this is a safe place. Money is no object. The check's in the mail. Let's get creative. But you have already gone way ahead on all of these. What about a mirror? Like, you've got this sheet of mylar that's covering the liquid and is degrading the optical quality a little bit. If you're bouncing the light from some distant object off of a mirror, are you back to even if it's a flat mirror, are you back to having to essentially grind that mirror perfectly?
Yeah. I get this question all the time. People ask, why don't you just use a big flat mirror that you can steer to reflect the light down to your telescope? Then you could look anywhere.
Yeah.
And the problem is, well, that would work, except the cost of making that mirror would be orders of magnitude more than the cost of the liquid mirror telescope, because you have to make the surface optically flat and you have to keep it optically flat, right, even as you're tilting and the gravity is changing and the temperature is changing. It's just really difficult and really expensive.
And so you might as well grind a mirror of the size that you're hoping and just call that a telescope instead. Yeah. So then, I mean, we've gone for flights of fancy, and let's talk about sort of what you think is actually going to happen. So you've got first flight just happened in India. So how is when will people start to see some papers coming out of some of the research that you're doing?
Yeah, probably not. Well, there'll be papers about the technology, but science results probably won't be till next year. So right now, they've in fact just stopped the mirror because the monsoon season is here. And it has to be, all of the telescopes get shut down during the monsoon because the humidity is close to 100% and it's raining a lot. And then everything wakes up again in late September at the end of the monsoon. And so we're planning to restart the telescope probably in October. We want to do some adjustments to the corrector lens, and that will be done in early October. Once that's all done, we start up the mirror. We do some more alignment checks, engineering tests. And once that's completed and we're happy with the image quality, then we'll just start collecting data. And in the meantime, between then and now, the team is busily working on the software so they can be ready for this stream of data that will come once the telescope starts science operations.
And we got, today, we got the third release from the Gaia mission. Yeah. And it was this giant dump of 1.8 billion stars in the Milky Way and so on. And
right.
And will you probably go in the same way and just like the Sloan Digital Sky Survey, just release all of your data and then let the research community start digging through it?
Yeah. So we'll release the data. I think we're still discussing whether there should be a proprietary period, but if there is, it will be very short. So we plan to make all the data available publicly, and also probably some of the software that we would use to at least, so we would make pre-processed data available so the instrumental effects are being removed.
So are there any other shapes? Are there any other situations where spinning liquid metal, are there any variations on this idea? You talked about the moon. Is there anything else out there that you think might make sense that you guys have considered?
Yeah, there have been some concepts proposed for, say, free-flying telescopes. And you might wonder, well, if it's free-flying in space, there's no gravity, so how could you make a parabolic mirror? And the idea is that you would have a solar sail that would constantly, slowly accelerate the telescope. That would provide the equivalent of a gravitational force. And then you would rotate it to make a dish, and it would then be looking in the direction in which it's going, basically. And you could make quite a large sort of parasol that way with a large collecting area. Now, none of these things have been studied in great detail. Nothing comparable to what we did for the Lunar Liquid Mirror Telescope.
But the acceleration by a solar sail is equivalent to the acceleration of gravity. Thanks, Einstein. Yeah.
Yes.
Yeah. You literally you've thought of everything. I am so stoked on this idea and what's coming. So then, if people want to keep track of of the team and the project, what's the best way for people to see what you're doing?
Probably just going to the website. It'll get updated periodically. And you can just Google International Liquid Mirror Telescope, and that will give you, it'll pop up the website in Belgium, which is the main headquarters for the project.
Fantastic. Wonderful. Well, Paul, thank you so much for taking the time to chat with me today. It was really eye-opening and exciting, and I was not expecting it to go to the places that it did, and I'm really glad that you have deployed this telescope and are working on future and even bigger versions of it, especially the one that's going to be on the moon. That sounds great. So, and the one in every, perched around the world, to give us that full real-time version of the sky. That sounds wonderful. Thank you so much for taking the time to chat with us today.
It's a real pleasure. Thank you.
Take care.
Bye.